Alright, here we're going to take a look at a thermal expansion problem, this time using plane stress elements. And in fact, it's the same plane stress problem that we have in another video. And so for that reason, when we go through the Excel input sheet, I'm not going to redo all the nodes and everything because we already did it. So here you'll notice that this is the same nodal information that we have from the other plane stress problem. Moving on, we still don't have any line elements, still don't have any spring elements. Now I kept all the information that we had from our triangular elements as written before, but what I'm going to do is change the coefficient of thermal expansion because now it matters. Now we have a change in temperature. We have an initial temperature and a final temperature, and so because of that we're going to go ahead and make sure that we enter in our coefficient of thermal expansion. So we'll go ahead and move over here and we'll just go ahead and enter 22 times 10 to the negative sixth. And we'll go ahead and say that's the same for element 1 and element 2. Alright, and that's the only change. Otherwise, it's the same things. We enter in our nodes in counterclockwise order, enter in our elastic modulus, Poisson ratio, thickness, all that stuff. The only thing is now, since it's a thermal problem, we also need the coefficient of thermal expansion. Alright, and it turns out this coefficient of thermal expansion is the same as for quadrilateral elements. So we'll go ahead and enter that in here as well. And we'll move on to our temperature, and here it actually does matter. And we can actually describe a temperature for individual nodes. And this is because a lot of times you have a mapped temperature distribution. So in this case, we just have one temperature, and we'll go ahead and look at what it says here in our notes here. So if we enter in a 0, that will set the default temperature for all nodes that do not have specific temperatures assigned. So we have a uniform, what we might call a temperature or a thermal soak. And so for that reason, I'm going to enter the number 0 here. Okay, there is no node 0, but the node 0 says, hey, this is for every node. And so we're going to go ahead and say our first initial temperature is 20 degrees Celsius, and final temperature is not 199, 100 degrees Celsius. And keep in mind that when I say these units, we don't enter in any units in this, right? It's up to us to keep track of the units. Okay, so we have our thermal soak condition, we have our thermal expansion created, we have our constraints. Those are the same as before, so we're not going to change that at all. We still do not have any nodal loads, distributed loads. We did have pressure loads. I already deleted them from the last problem, so we won't have those as well. Now you can have a mechanical load, such as a pressure load and a thermal load applied simultaneously. In this case, we don't for this example. Alright, with that, we'll go ahead and save it. Close it down, minimize that, open up our FEA 2D solver, and let's see, it's referenced in the old problem, so we'll go ahead and say that now we want the one that has thermal expansion associated with it. And with that, we'll go ahead and scroll down. We do have units of Celsius for temperature. That's important because that's what we use for a coefficient of thermal expansion and our temperature references. We still want a text file for our results, graphical plots, and we'll go ahead and still keep our element and node numbers on there. Alright, with that, we'll go ahead and save it and solve it and see what happens. Alright. Go ahead and scroll on down, and sure enough, boy, it really loves keeping these old results from an old problem done a long time ago. Well, we just go ahead and click that open in a new figure window so we can see what's actually happening. And here, just as we expect, we see that it's not just expanding out this way, right, but it's expanding everywhere, right? And that's what we would expect when we have thermal expansion. It expands uniformly, right? And notice something else interesting. Let's go ahead and we'll keep this open to the side here. We'll scroll on down and click this. Pardon me, let's see. Is that going to open in a new window? Here's our von Mises stress results. And look how small that value is. It looks a little bit odd, but if you look at that value, 1.5 times 10 to the negative 7th, that's almost 0, and that's what we want because we actually have constrained this problem such that, we'll go ahead and open up our problem here. We constrained it so that it could easily expand with this roller constraint at node 7, it could easily expand this way. It's free to expand out this way. And so this whole structure can maintain its original geometric shape without any distortion. It will expand, right? Now the size will change, but the shape will stay the same. It will still remain a square shape as it expands due to thermal expansion. Now this is an example of what we would call kinematic constraints, right? Where it's allowed to expand freely and without being over constrained. All right, so now we'll go ahead and go back to our MATLAB here and scroll down and see what else we have. I think this last one is just going to show us element quality, which we discussed in the other plane stress video. So we'll go ahead and shut that down. Okay, once again, we go ahead and take a look at our text file results just to verify if things make sense. And look at this, total applied load. We actually don't have any real applied load and just numerical error in terms of reacted loads. Now we do have a temperature assignment, and so that's included here. Let us know that there is something happening, right? Even if there isn't a mechanical load, there is a thermal change, and we can see all the displacements, and so just as we expect, it's expanding out in the x direction linearly for nodes 1, 2, and 3. Nodes 1, 2, and 3 all go down as we would expect, right from that free expansion that we talked about earlier. Okay, we have the same thing, 7, 8, 9 going expanding upwards, and if we go ahead and look at that, that's indeed what we see over here as well. Okay, so now this is interesting. This is interesting, right? Where we have our total applied loads and we have our total reacted loads. Interesting. How do we interpret this, right? How do we interpret the fact that we have this applied load at what looks to be the nodes 1, 4, and 7. So that's on our x side, right? So we have this negative 88,000, negative 88,000. And so what we should emphasize is when we say the total applied load, right? This is all done internally within FEA in a way to interpret our nodal loads, our nodal temperature loads. In the FEA solve process, it actually turns those into a representative mechanical load, and so that's what's actually being done. So it takes these and represents them as mechanical loads, and from those mechanical loads, that's actually what we're seeing over here. These are representative mechanical loads, but they are not really what's being applied, right? They're not really what's being applied. And so with that, we can see that our total reaction indeed is 0. All right, it's all just numerical error. Okay. Now we have, in fact, we can see down here a little bit better distribution of what's happening, right? These are thermally applied loads, so that's all just representative of thermal loads. And for a better discussion on that, we need to get deep into the theory of it. Okay, so now we have stress results, and we'll notice that almost all of our stress results are 0, and that's for the reason we mentioned earlier. They are almost all just expanding freely due to those kinematic constraints. All right, so I think that will cover it. Just remember, if you do want to go deeper to figure out, hey, what's happening when I set up this problem, you want to try to understand what's happening with elemental matrices, you can check those out. Global matrix formulation, if anything about the details that are typically hidden in a normal software solution like ANSYS or FEMAP or Nastran, things like that. Well, now you can go in here and dig in that a little bit. All right, but with that, that's all we have for our thermal expansion problem. Thank you.